Let's make one more exercise on basis of R3. So far we have found in the previous exercises several bases of R3 according to certain characteristics or prescriptions we wanted these bases to have. Now, increasing the difficulty, we will consider the following situation. So find the basis of R3 containing the vectors of some bases of the subvector spaces A and B. A is defined to be the subvector space. Well, we define it as a subset, and by previous exercises we have shown the subsets with these descriptions are indeed subvector spaces of Rn. So in this case the subset A is comprising the triples x, y, z in R3 such that x minus 2y plus z equals to 0, and B is such that minus x plus y plus z equals to 0. So what does it mean, find a basis of R3 containing the vectors of some bases of the subvector spaces? So more precisely what we are meaning is this. So in other words, we want to find a basis which at the beginning we call it D, the basis of R3 we are looking for, with vectors v1 through vn, and two subsets dA in D and dB in D, such that dA is a basis for A and dB is a basis for B. So let's see one possible strategy. One possible strategy is to start with finding a basis VA for A and VB for B. Now, second step is to see if we are lucky, which means that we are able to find the basis D we are looking for by completing the union of VA and VB to a basis of R3. So in this case, if we can complete VA union VB to a basis of R3, then, well, certainly inside D we will find two bases, one of A and one of B, namely VA and VB inside. Okay, now, so if we are lucky, we are done. Now, if we are not lucky, so we are not able to find a completion of VA union VB because we don't know yet, but we have to check. Possibly we cannot complete it to a basis of R3. Then step number 3. Well, so if this is not possible, use the vectors in the union VA union VB to create somehow basis dA and dB with the sought properties. Okay, so we have to change somehow the basis VA and VB and find new basis dA and dB, for which we can actually extend or somehow complete it to a basis of R3. And then inside this basis D we can find dA and dB. So let's start from step number 1. So A, by definition, is the following set. Now, in a previous exercise, namely exercise 1.1, we have already found a basis of these. Well, we have proven that this is a vector space of R3 in this case, and actually we have even found a procedure to determine a basis of A. Okay, so by exercise 1.1 we know that this set is a subvector space of R3, and a basis can be found as follows. Well, we rewrite A implementing the equation defining A inside the notation of the generic vector of R3. So we can explicit Z in this case in function of x and y. Therefore, we can rewrite A as the set of vectors in R3 given by the coordinates x, y, which are unrestricted, and then z is not going to be unrestricted, but is going to be subject to the following rule. So z will have to be 2 times y minus x. Now in this case, in this form, we can easily find two linearly independent vectors inside A by choosing first x equals to 1 and y equals to 0. So we are free to choose x and y completely unrestricted. So let's, for example, choose x to be 1 and y equals to 0. Then the third coordinate will have to be 2 times 0 minus 1. Okay, so in this case we find the vector 1, 0, negative 1, and then choosing x to be 0 and y equals to 1, we'll find the vector 0, 1, and then 2 times 1 minus 0, which is 2, 0, 1, 2. Now we found two linearly independent vectors inside A, while it can be easily shown that these are also generators of A. So any vector in A of this form, which is a vector of this form, is a linear combination of these two vectors. For example, this is a generic one. And what is the linear combination of VA, of these two vectors in VA, to get the xy 2y minus x? Well, it's precisely a linear combination with first coefficient x and second coefficient y. So if we take x times 1, 0, negative 1 plus y times 0, 1, 2, we'll precisely get this generic vector of A. So these are also generators, so they are a basis of A. And then this is explicitly done in exercise 1.3. Now, similarly, we can find that VB has a basis 1, 1, 0, and 1, 0, negative 1, exactly in the same way. So we will not repeat it. Now let's see if we have been lucky with the choice of these two bases, VA and VB, and see if we can extend the union of VA and VB to a basis of R3. So step number 2, we'll divide step number 2 in two sub-steps. So sub-step A, by the basis extension theorem, which has been covered in lecture 5.4, we know that a basis of R3 must have just 3 vectors. Okay, so the basis D we are looking for will contain 3 vectors, but the union of VA and VB, as you can see, contains 4 vectors. They are all different, so this is a set of 4 vectors, so they cannot be all linearly independent, always by the basis extension theorem. So in a vector space of dimension 3, like R3, we cannot find 4 linearly independent vectors. Therefore, they cannot be linearly independent, and a fortiori they cannot be completed to a basis of R3, because a basis is a set of linearly independent vectors and generators, but they are not linearly independent to start with. So certainly they cannot become linearly independent if we add more vectors. Okay, so we are precisely in the case in which we have not been lucky. So the union of VA and VB cannot be completed to a basis of R3. Now, what we can wonder now is if actually these are generators of R3. So if we cannot complete it to a basis of R3, maybe if they are generators of R3, then we can extract a basis of R3 inside the union of VA and VB. Okay, so that we can extract the basis of R3 from VA union VB. So at least we can find a basis of R3 that has somehow something to do with A and B. Now actually the answer is yes. So the union of VA and VB is a set of generators of R3. How do we see that? So one way of checking this is by forming the matrix M, in which the M is defined by the vectors of VA union VB as columns. So as you can see here, the first 2 columns are the basis VA, and the second 2 columns are the basis VB. Let's call this matrix M. So we reduce this matrix in row echelon form by operating with row elementary operations. So we know that the resulting matrix will have columns, and the linear relationships between these columns will be exactly the same linear relationships that we have in the columns of the initial matrix. These facts have been stated and defined in lecture 6.7. We start from M, and then after applying a row elementary operation between the first row and the third row, we reduce this matrix here, and then we apply another elementary operation in which we kill the number 2 here, the coefficient 2 here, by means of the 1 here. And we finally get to this matrix, which is in row echelon form, as we can see. And in particular, we see that the first 3 columns are linearly independent. And so since the first 3 vectors of this matrix are linearly independent, we conclude that so are the first 3 columns of M. Because we operated with row elementary operations, therefore the linear relationships between columns remain unchanged. So summing up, we have shown that the vectors 1, 0, negative 1, 0, 1, 2, and 1, 1, 0, which are the first 2 are the basis of A, and the third is the first vector of a chosen basis of B, is a basis. So this set of 3 vectors is the basis of R3. But unfortunately, this is not the basis D we are looking for. Why is that? Indeed, while it contains a basis of A, because the first 2 vectors constitute the basis of A, it does not contain a basis of B. But because there is one vector of the basis of V, but none of the first 2 vectors are inside B, because none of these 2 vectors satisfy the equation defining B. Therefore, we are back to the initial strategy, and we have to go to step number 3, because we are in the situation in which the basis we found, even the new one that we actually found a basis of R3, not completing the union of VA and VB, but extracting a basis from them, even that one is not an appropriate basis. So step number 3. Now, what we are going to do, we use the data we gathered so far to produce the basis we are looking for, the basis D. Okay, now we have plenty of bases. We actually define the situation more clearly, figuring out the dimensions of the subspaces and the spaces involved. So now let's try to put everything together and see how we can find our basis D. Now, since the basis for R3 must have 3 vectors, and A and B have both dimension 2, we necessarily must have one vector of D which lies simultaneously in a basis of A and a basis of B. They have dimension 2. We have seen that each of them must have 2 vectors. Each basis must have 2 vectors, but altogether must be 3 vectors. They must be 3 vectors. Therefore, what we can try to do is to find these 3 vectors, one of which is in a basis of A and in a basis of B. That brings up the role of the intersection of the vector space intersection between A and B. That brings up the role of the vector space A intersected B. So the result we use to get information on A intersected B is the following one that we already used in exercise 1.3. It is Grassman Theorem. Relates the dimension of the sum of 2 subvector spaces with the dimension of each of the vector spaces and the dimension of the intersection. Okay, so this formula applies. Now, in the previous point, in the step number 2, we have actually found a subset of 3 vectors in VA union VB, which constitutes a basis for R3. Therefore, the vector space A plus B must be all R3, and its dimension is 3. Now in this formula, if you plug in 3 here, and we know dimension of A and dimension of B being 2 each, then we have 3 equals to 2 plus 2 minus something we don't know a priori. Therefore this must be 1. So dimension of intersection must be 1. Now let's suppose that we found a basis for A intersection B, and so the basis must be constituted by just one vector. We call it V with the subscript A intersected B. Then if we find other two vectors, one we call VA in A and one VB in B, both of them independent with VA intersected B, then we can define D to be the set of vectors VA, VA intersected B, and VB, and we can prove that this is the basis we are looking for. Indeed, well, so we have to prove that D contains a basis of A. Well, we know that VA and VA intersected B both are vectors of A, and they are linearly independent. Therefore, they are a basis of A. We know that A has dimension 2, so if we find two linearly independent vectors in a vector space of dimension 2, then they are a basis, because they're also generated. Then we can find also a basis of B, namely the subset comprising VA intersected B and VB, for the same reason why this is a basis of A. So the last thing we need to check is that if indeed this is the basis of R3. Okay. But this is the basis of R3 because all three vectors are linearly independent. Now VA and VA intersected B are linearly independent by assumption, but also VB does not belong to A. Why VB does not belong to A? Well, the only way, if B belongs to A, since it belongs to B, it must be in the intersection of A and B. But the intersection of A and B is generated by just one vector. And this vector is VA intersected B. Therefore, if VB belongs to A, would be a multiple of VA intersected B. But by assumption, we picked VB linearly independent with VA intersected B, therefore cannot be a multiple of it. This shows that VB cannot belong to A. Therefore, it is a vector that does not belong to this subvector space of dimension 2, and since the vector space where we are living has dimension 3, which is 3, these three vectors are linearly independent and are a basis. So let's find the basis of the intersection. Now, the intersection of A with B is the set of triples x, y, z in R3, such that both of the equations x minus 2y plus z equals to 0 and minus x plus y plus z equals to 0 are satisfied at the same time. Now, we talked about these kind of sets in exercise 1.3, and there we even showed how to find basis for these subvector spaces. So what we can do here is again implementing in the very writing of the generic vector of A intersection B, the equations one at a time. So first we implement the first equation, and so the writing becomes triple of vectors x, y, and z is forced by the first equation to be 2y minus x, and still there is one more equation to be satisfied by these triples, which is the second equation. But the second equation, there is a z in it, in the expression, but the z is in function of x and y from the first equation. So substituting, plugging in the value of z that we get from the first equation, well, the second equation reduces to minus 2x plus 3y equals to 0. So we have this equality, A intersection with B is this set. The next step is to implement this equation inside the writing of the generic vector once again. Here we can express y in function of x. The generic vector will no longer be x and y left free to vary, but it will be x free, and then y is going to be depending on x. So it's going to be 2/3 times x, and z, well, z is 2y minus x, but once again implementing the relation that we have expressing y in function of x, we are reduced to 1/3 times x. So A intersection B can be expressed as the set written in the following form. The generic vector will be x, 2/3 x, and 1/3 x, where x is left free to vary unrestricted. So from this writing we can just, we know this is a vector space, so we can just take any non-zero vector inside here, and that will be a basis of A intersection B. For example, let's pick x equal to 1, and we get this vector 1, 2/3, 1/3, and this is a basis of the intersection of A and B. Second step is, so we know now, we found the vector V8 intersected B, which is this. Now let's find VA and VB. So how do we start looking for VA and VB? Well, we have already two bases of A and B, and why don't we start from them? So just look at their bases previously determined. So A was the vector space generated as a basis by 1, 0, -1, and 0, 1, 2, and then B generated by 1, 1, 0, and 1, 0, -1. Let's just pick VA to be just the first vector of the basis of A, and VB the first vector of the basis of B, and see if they work. So they're certainly not multiple of VA intersected B. So remember that the conditions, now they are gone up the screen, but the conditions we want VA and VB to satisfy are that there's just one, is that VA is linearly independent with VA intersected B, and VB belongs to B and is linearly independent with VA intersected B. So when two vectors are linearly independent, when one is not multiple of the other. So we just want to check that VA is not multiple of VA intersected B, and VB is not multiple of VA intersected B, but this is obvious. By what we have said before, the set D given by the vectors 1, 2/3, 1/3, which is the vector VA intersected B, the vector 1, 0, -1, which is the vector VA, and the vector 1, 1, 0 are a basis of R3, and the first two are a basis of A, and the second two are the basis of B. So this is precisely one of the bases we were looking for, and the exercise is solved.